So now looking at number 2, this is where the hummingbird starts from rest and accelerates at a constant rate. So a constant rate here does not mean that velocity is constant. It means acceleration is constant, right? From v equals 0 at t equals 4 to v equals 4 at t equals 2, and we're supposed to sketch a graph of the velocity function, all right? So another way we could say that, we start from rest. So this statement here, starting from rest, is the same as saying v of 0 equals 0. So rest means the velocity is 0, starts means t equals 0. So v of 0 equals 0 is the same thing as saying starts from rest. All right, now, so let's try to make a sketch of that. So for our part A, we're going to make a sketch of the velocity curve. So here's 2 and here's 4. So starting from rest means this time the acceleration does start at 0. And we know that v of 2 equals 4. And then it accelerates at a constant rate. So, you know, we can think of what that means a little bit, that the acceleration is constant. And so it's worth thinking that since a is equal to v prime, that means a is the slope of the graph of v of t, and that means that since a is constant, that means that the slope of the graph is constant. So in other words, means we have to have a linear function for v. In fact, it's probably not too hard to figure out that v of t equals 2t. All right, let's see. What are we supposed to do next? Okay, yeah. Part B is find the area under the curve from t equals 0 to t equals 2. So here's that phrase, area under the curve again. So part of the thing that we're going to be getting used to is we're going to be spending a lot of time finding the area under the curve, which in this case is velocity curve. So partly, you know, just paying attention to what that means is I'm looking at, this is my velocity curve. It's a straight line, but we're going to still call it a curve. All right, and there you go. There's your area under the velocity curve. So area equals 1/2 base times height. So that's 1/2 times 4 times 2, which is 4. All right, if we look at the units again, the time, this is the time axis. Time is in seconds, and this is the velocity axis when the velocity is in meters per second. So even though I'm looking at an area, it's an area where each of the distances carries a unit. So I could think of that area as being 1/2 times 4 meters per second times 2 seconds, and that equals 4 meters. So that, again, is just a way of doing a unit analysis on that. All right, then part C. If you are in physics or you've done physics, and you probably know this formula, x equals 1/2 at squared. If you don't, then now you know. This is how you get the position. And by the way, we're going to find out why this is the case in this class soon. So x of t is equal to 1/2 at squared. And our job is to use that to calculate. Let's see, let's get my ABCs in order here. This is part C. We're going to calculate the distance traveled. So the distance is the x of t. So we could say it like this, x of 2 equals 1/2. We need to find out what this a is. Okay, well, a is the slope of the graph. All right, we already figured that out. What's the slope of this graph? If I think of the velocity equation as 2t, all right, then that slope is 2. All right, so it equals, the slope of the graph is 2. All right, so that 2 is my acceleration, which I can put here. All right, and then I go times squared. Time is 2, so times 2 squared, which turns out to be 4 meters. So I can put in the units again and look at this as being 1/2 times 2. Acceleration is measured in meters per second squared times 2 seconds squared is equal to, well, actually that's a lie. It's times 2 seconds squared, right? So then we square the seconds and then they cancel. So then we get 4 meters. Yeah, I thought there would be something kind of interesting about how the slope of the graph, right? The slope of the graph is going to be think of the slope as being y2 minus y1 over x2 minus x1. So it's going to be meters per second over seconds, meters per second squared. So that's how we could know from looking at the graph, too, in terms of unit analysis, that unit of acceleration is 2 meters per second squared. Okay, so that equals 4 meters. A couple other things that they ask us to do, but first I think I wanted to break this equation down and look at a couple of things that are interesting that sort of pull out of the relationship between this equation and this equation. Right? So if I consider, what does acceleration mean? Acceleration means the change in velocity over change in time. This is a formula that we can use for constant acceleration only. And of course, where we're headed with this is if the acceleration is not constant. But in this problem, the acceleration is constant. So acceleration is delta v over delta t. So I could rearrange this and drop the deltas and notice that v is equal to at. So just like here, our v of t is equal to 2t. So if I think generally, with any constant acceleration, the velocity is equal to acceleration times time. If I start from rest, because this is also, a y equals mx plus b, so we're assuming that the y-intercept here is 0, or I guess we'd say the v-intercept is 0, means we started from rest, from velocity 0. All right, then with this in mind, if I think about that area of the triangle being 1/2 base times height, and then look at where the base and the height are on this graph and what they represent in terms of time and velocity, the base of the triangle is the amount of time that the object has been moving. So it's a hummingbird in this case, it could be anything. All right, and then the height of this triangle is going to be the velocity at that time, the velocity at the end of the interval, which is equal to at, acceleration times time. All right, so I can look at this area under the curve as being 1/2 times t times at, which is 1/2 at squared, which suggests why, for constant velocity, the area under the curve is going to be the same as the distance traveled. All right, and we see that in this specific instance where the area under the curve is equal to the distance traveled. So once again, area under curve is equal to distance traveled. The area under the velocity curve. All right, so far, and there's one more thing in this. I guess let's go ahead and throw that in there. It says in part D to verify that the acceleration is constant by finding the second derivative of x of t. So I have x equals 1/2 at squared. I had a couple of people in some other classes include the a equals 2, but let's keep the a general and say, let's say for any a, then x prime is equal to at, because again, we've seen a couple of problems where the book and the AP exam like to keep constants expressed as variables within a problem, but they're constant with respect to this problem, right? A is constant. We're using a variable to represent it because it's not specified, but it's a constant with respect to the derivatives that we're doing in this problem. So then x double prime is equal to a, so we get not only that a is constant, but it is the a of the equation 1/2 at squared, all right? So that is constant because it does not depend on t. All right, that's part D. Now we're going to start talking about part 4, number 4, which is really going to lead us into the calculus part. Notice we have not done any calculus yet. We've done geometry and very basic physics.